Okay, so in this second video, I'm going to go over the second law that you can use to find the magnetic field from a current carrying wire, and that is Ampere's law. So Ampere's law is, as I mentioned in the first video, it's a shortcut for finding the magnetic field. And so let me just write this. So it's a way of finding the B field from a current carrying wire. Using symmetry. Okay, there has to be symmetry in order for this to work. Okay, and there are really three main symmetries. Long straight wires, so wires which are long and straight. Solenoids and toroids. Oops, toroids. So I'm just going to go through and basically derive um, the B field equations that I wrote out for you in the first video. I'm going to use Ampere's law to derive each of the formulas for these three symmetries. Okay, so let's first look at Ampere's law. So this is Ampere's law here. And remember I mentioned it's very similar to Gauss's law. So you've got like a left-hand side of the equation and a right-hand side of the equation. And you're setting them equal to each other, and then you're basically solving for the B field. So on this side of the equation, the left-hand side is just the line integral around a closed path or like loop, which you pick, which you uh, choose. Okay. And this is the closed loop is referred to as an Amperian loop. And it's similar to Gauss's law where you can draw any loop that you want. Okay, so like just like you draw your Gaussian surface, and then you're looking at like the electric field lines that the flux that goes through that surface. Here we're drawing a loop, and then we're integrating along that path, which is where the path integral comes in. And the line integral, which is the left-hand side of the equation, the line integral around that path equals the right-hand side, which is just the enclosed current. So it's sort of like in Gauss's law, the Q enclosed. Okay, and it's just times a constant. Okay, so let's see like what this looks like with the simplest case, which is a wire. Okay, so let's say I have a long straight wire which carries a steady current of 40 amps, and I want to know the magnitude of the magnetic field at a distance 4 centimeters from the wire using Ampere's law. So like again, it's important to note that you could just um like go straight to this formula. Okay, this formula is like tried and true for a long straight wire. Okay, you can get there through the Biot-Savart integral or through Ampere's law, which is what we're doing now. Okay, so we're going to arrive at the same result as we did in the first video. This is just a different way of looking at it. Okay, so let's draw the wire. So say I have a long straight wire. And when this is long, this is sort of code for you can use the wire symmetry. It's almost like it's like infinitely long. Okay, it's like it gives you a clue that you can use the symmetry in this way. So the current is going through, let's say it doesn't tell us which direction, so we can just pick it. So I'm going to point my thumb in the direction of the current, and I know the B field is going to be coming out of the page above the wire, and into the page below the wire, right? It's gonna form basically these. Let me draw it a different. Actually, sorry. I'm gonna draw it a different color just to be clear. Okay, so it's coming. So point my thumb in the direction of the current. It's coming out of the page above the wire, going into the page below the wire. Okay, so it's forming these closed loops around the wire. Okay, like, all right, I mean, it doesn't look great, but you get what I mean. So out of the page above the wire, into the page below the wire. Okay. So and I'm interested in knowing the B field a specific distance away from the wire at 4 centimeters. So let's just say, for argument's sake, and let me just label this B field. So the B field is in the orange. Okay. Let's just say that this loop here, this B field loop here is a distance of R, right? Which is 4 centimeters. Okay. So the strategy for Ampere's law is I draw my Amperian loop exactly where I want to find the B field. So I would draw my Amperian loop, let me make it black, like at that distance. Okay, and I'm going to make it a dotted line because we know it's not actually there. It's not real. It's just like a construct that I'm using to make the calculation easier. Okay, so that's like that dotted line is my Amperian loop. Okay, and you'll notice that like the direction of the loop is in the same direction as the B field, right? Like if I were to draw like little vectors representing, they're parallel to each other, which is what I want with a line integral, right? I want to integrate, I want the B field to be pointing in the same direction as my Amperian loop all the way around that path. Okay. Which is the case. So that's why I chose it as a loop, if that makes sense. That's how you decide like what the shape of your Amperian loop is. So you draw it such that the loop follows the B field path. Okay, so that the line integral is very simple. Okay, so I'm going to write out the equation. So I know that Ampere's law is the line integral of B dot dl is equal to mu naught I enclosed. Okay, so this line integral is super easy. It's just B times the perimeter, like the path around the circle. So that's just like 2 pi r, right? If I go around the perimeter. And so that's going to equal mu naught I enclosed. Okay, and now I solve for B, right? So this is mu naught I enclosed divided by 2 pi r. And that is the same equation that we got that we had way up here, right? It's the same equation here. Okay, so that's like, and I mean, again, like it's the sort of thing where you don't go through this necessarily every single time. You sort of just like see a straight wire, a long straight wire, and you say, oh, like I know this is the equation for the B field at a certain distance r away from that wire. Okay, if I plug the numbers in, I mean this problem did give you numbers like 40 amps, r is 4 centimeters. This is just a constant, pi is a constant. If I plug the numbers in, I should get something around 3 micro Tesla. You can kind of try that out on your own. And the direction, we should say, the direction is defined excuse me, is defined by the right-hand rule. So, I mean, however you want to describe that, it's basically what I drew here. It's coming out of the page, above the wire, into the page, below the wire. If I'm looking at it from the right, it's clockwise. If I'm looking at it from the left, it's counterclockwise. I mean, however you want to say it, as long as you draw it clearly is fine. Okay, so that's the wire. Let's talk about the solenoid. So here's the second example. So let's say I have a long solenoid. It has 1,500 turns per meter. Okay. And it carries a current of 0.8 of an amp. And I want to use Ampere's law to find the magnetic field inside the solenoid. Okay. So with a solenoid, remember what a solenoid magnetic field looks like. If you remember from the last module, like let's say that you've got this coil of wire, right? And you've got this magnetic field that goes, you can kind of imagine like the middle of the solenoid is where all the magnetic field is concentrated, right? And then you've got some field out here. Okay, but the field outside mostly cancels. Okay, so it's really only inside the solenoid that you have to deal with. Okay, when you're thinking about a solenoid. Okay, so the black lines here represent the magnetic field line. And again, like if I curl my fingers in the direction of the current, then my thumb indicates the direction of the magnetic field. So in this picture, the magnetic field is pointing to the left. So I'm gonna draw. Okay, so let's write out my formula. So for Ampere's law, so the line integral around some Amperian loop is equal to I naught times I enclosed. But I have to pick my Amperian loop in like a smart way, right? So I know that my B field is going like in this direction in the middle of the solenoid, right? And in the solenoid, in the middle of the solenoid, this field is uniform. Okay, I remember that was one of the things that that you learned in the tutorial. It's a uniform field. So it makes sense to draw my Amperian loop just like a rectangle. Okay, so this is my Amperian loop. Okay, and it's really only this part of the loop that has any B field to dot product. Like the only contribution to this is going to be from from path B. Well, I guess I mean it's this one. So from A to B. Okay? Because from B to C, the path from B to C is perpendicular to the magnetic field. Okay? So the path from B to C, and similarly from D back to A, like this is equal to 0 because the B field is perpendicular to the path. Okay, like as I go around the loop, these sides don't contribute anything. Okay, so the path from C to D, this is also 0 the dot product between the line integral along that path is also equal to 0 because the B field out there equals 0. Like outside the solenoid, the B field equals 0, like over here and over here. It's really only in the center of the solenoid that there's any B field to speak of. So I only have to like take this like little segment of the path into account when I calculate out like the left-hand side of this line integral. Okay, so that's just going to be so let me write it. Let me rewrite it over here because I've kind of run out of space. So B dot DL equals mu naught I enclosed. So this just equals B times L, right? Where this is L. Like we're calling the length like here L. Okay. And then now we have to figure out like what I enclosed is. So this is the only other kind of tricky thing. So we're given in the problem the number of turns per meter. Okay, so I enclosed is going to equal N times L times I. Okay, because this N times L is the number of enclosed like loops. Like it's the number of loops that go like that are enclosed by my Amperian like path here, if that makes sense. So it's like basically like counting up like 1, 2, 3, 4, 5, 6, 7, 8, 8 loops, right? N times L is the number of enclosed loops because like we're given the number of loops per meter, right? So if I multiply that number by L, it gives me the number of enclosed loops, and then each of those loops has a current I. Okay, so I enclosed is just NLI. So this is going to equal mu naught times NLI. And then I just solve for B, right? So B is mu naught NLI divided by L. That cancels with that. So that's how I get mu naught NI. Okay, so this is the magnetic field for like a very long solenoid. Okay, and again, if we just like want to keep ourselves honest, like if we go back to the very beginning here, it's this equation. Okay, mu naught N times I. Okay. All right, one to go, the toroid. Okay. Oops. Oh yeah, so all the way down here. Okay. So this one's very similar. The only difference is like the geometry is slightly different. Okay, so like remember I said in the first video, what is a toroid? A toroid is like if I took this solenoid and I made it into a donut. So imagine that you have like a long flexible pipe and there's a wire going all the way around the outside of that pipe. Okay. And I know that the B field is going through the middle of the pipe. And then I took that pipe and I like twisted it into a circle. Okay, like I think it's easy to see that the B field, if you did that, would just be totally inside the pipe, right? So like this is sort of like just using my analogy. Like this is kind of like the pipe, right? And this is the wire. So this is coming like out of the page into the page, out of the page into the page, out of the page. So the wire is like going like this in 3D. I mean, it's hard to draw, right? So inside the toroid, there's this magnetic field. And unlike the solenoid, it is dependent on like how far into the coil you are. Like there's this R dependency that actually doesn't exist with the solenoid. Okay, remember we said that the solenoid, the field is uniform. It doesn't matter like where you are inside the solenoid. With the toroid, that's not true. Okay, like if you're the R, it's got an R dependency. So let's derive this one. So we're going to start with the same place. So the line integral b dot dl equals I enclosed mu naught. Okay, so I enclosed. So I'm going to draw my Ampérian loop such that it encloses like, okay, so like let's say I want to know what the magnetic field is right at this point here, right where I drew the dot, because I mean that's R. So this blue line here would be my Ampérian loop. Okay. So that's my Ampérian, the dotted line is my Ampérian loop. I have, with that loop, I have enclosed all of the turns. Okay, unlike the solenoid where I've only enclosed the turns that are part of my, like, that are enclosed in my Ampérian loop of length L, right? Which is why there's this, like, this expression here. With a toroid, I draw it like inside the toroid. So my I enclosed is just the number of loops times I. Because this dotted line encloses all the loops. Okay, so like because your Ampérian, which is not true of the solenoid. This is like the only difference in my mind. The Ampérian loop encloses all n of the turns of the toroid. Oops, of the toroid. Okay, and each loop carries a current I. Okay, so the line integral. So a question that you have to ask yourself is, does my Ampérian loop go in the same direction, like follow the same direction as the B field? And the answer is yes, right? My dotted black line it follows the exact path as this green arrow here, right? Like the B field is in the same direction, right, as my Ampérian loop, which makes this line integral simple, right? So the line integral is just B times 2 pi r, the perimeter all the way around that Ampérian loop, equals n I, right, from what I like figured out over here. So I just solved for B. So that's n I over 2 pi r, where r is like it's how far you are, the distance from the center of the toroid to the point that you're interested in, to the point of interest. But it's assuming that the point of interest is inside the toroid. Inside the toroid. Okay. So this is how you calculate the B field for a toroid. And that's pretty much it. I think it's a relatively light week this week, because last week, and the right hand rule would be you would use the right hand rule to figure out the direction of the magnetic field, right? You would just like point your fingers in the direction. I mean it's going to be, it's going to follow the same right hand rule convention that we talked about. So right hand rule direction will be determined by right hand rule. Okay, so that's pretty much it. That's all. It was relatively lightweight because we did like a lot of the conceptual stuff in module 7, and then this is just like how do you calculate the magnetic field, and the two ways. So the Biot survey and the Ampere's law. Okay, that's it.